In 1952, Boeing's president, Bill Allen, authorized a corporate gamble so extreme that his own board questioned it. The company committed millions of dollars to develop the 367-80, a prototype jet transport that would become the 707. Every dollar the company had ever accumulated, every factory, every patent, every future pension obligation, all of it was worth less than the cost of a single untested airplane. Engineers called it betting the company because that is literally what it was. If the aircraft failed to attract airline orders, Boeing would cease to exist. The 707 did not fail. It established the jet age and established Boeing's dominance for the next 7 decades. For most of commercial aviation history since, building a new airplane has followed a familiar pattern. A manufacturer identifies a market gap, invests heavily, delivers something better, and recoups costs over decades of orders. The cycle has repeated reliably. The 737 in the 1960s, the A320 in the 1980s, the 787 in the 2000s. Each generation replaced the last with something more efficient, more capable, more profitable. But today, that cycle has broken. Supply chains are fractured. Certification takes twice as long as it once did. Boeing carried over $54 billion in debt at the end of 2025. Airbus is capacity constrained at its own factories. Both manufacturers are facing supply chain fractures that have yet to close. The next-generation aircraft that now dominate global aviation, the Boeing 737 MAX and the Airbus A320neo, are evolutionary dead ends. Their airframes cannot be stretched, re-engined, or modified any further to meet the efficiency demands of the next 3 decades. The next clean-sheet narrow-body aircraft from Boeing and Airbus will together represent hundreds of billions of dollars in combined development costs and lifetime orders. It is the largest industrial decision in aviation history, and possibly the most consequential commercial bet any 2 companies will make this century. Boeing is drowning in debt. Airbus is years away from selecting an engine efficient enough to justify an A320neo successor. Development costs could reach $50 billion per program. Certification alone could consume half a decade. Yet, every airline on Earth is waiting. So, how can an industry that can barely deliver the airlines it has already sold possibly develop the ones it desperately needs? To understand why this decision matters more than any before it, we need to understand why the aircraft flying today have reached their absolute limits. The Boeing 737 first entered service in 1968. Its basic fuselage cross-section, its wing position, its landing gear height all date to the 1960s. Over 60 years since then, Boeing has stretched it, re-engined it, upgraded its avionics, and modified its flight control systems. The 737 Classic, the 737 Next Generation, which entered service in 1997. The 737 MAX began flying passengers in 2017. Each iteration squeezed a few more percentage points of efficiency from an airline designed before the moon landing. The Airbus A320 is newer but approaching the same wall. Launched in 1984, it introduced fly-by-wire controls to single-aisle aviation. The A320neo, introduced in 2016 with new generation engines, delivered a meaningful 15 to 20% fuel burn improvement compared to the A320ceo. It has since accumulated over 10,000 orders, making it the best-selling commercial aircraft family in history and surpassing its main competitor, the Boeing 737 family. But the A320 airframe, too, has been stretched to its structural limits. The physics are unforgiving. Aircraft that could accept larger, more efficient engines couldn't fit them under wings designed decades ago. Aircraft with modern wings couldn't maintain the manufacturing commonality that airlines demand. The trade-off seemed permanent, and then the 737 MAX disasters proved it wasn't just permanent, it was dangerous. In October 2018, Lion Air Flight 610 crashed into the Java Sea. 5 months later, Ethiopian Airlines 302 crashed in Addis Ababa. Both accidents killed a total of 346 people. Investigations revealed that Boeing had installed the Maneuvering Characteristics Augmentation System (MCAS) to compensate for aerodynamic changes caused by fitting larger engines onto a low-slung 1960s airframe. The system relied on a single angle of attack sensor. When that sensor failed, pilots were surprised that the aircraft pitched down on its own. Boeing did not tell pilots that MCAS was present on the aircraft. The aftermath reshaped the regulatory landscape permanently. Before the MAX disasters, certifying a new commercial aircraft variant typically took 12 to 24 months. Variant, not a new type. The FAA had delegated significant portions of the certification process to Boeing itself, trusting the manufacturer's engineers to validate their own work. That trust evaporated following the crashes and the Alaska Airlines Flight 1282 door plug blowout in January 2024. The FAA imposed a more rigorous oversight regime, which was relaxed with the current Trump administration. Certification timelines have now stretched. Boeing's own 737-7 and 737-10, relatively minor variants of an existing type, are not expected to certify until the second half of 2026, with deliveries beginning in 2027. The 777X widebody, Boeing's flagship next-generation long-haul aircraft, has been delayed so severely that it resulted in a $4.9 billion charge in a single quarter in Q3 2025. For any future clean sheet design, the implications are staggering. A brand new airframe with new engines, new materials, new manufacturing processes, and new flight control architectures will face the most intensive regulatory scrutiny in aviation history. Every system will require exhaustive independent validation. The era of self-certification is over. And this certification wall doesn't just add time, it adds billions in cost. Every month of delay means engineers on payroll without revenue, factories without product, and airlines without the aircraft they've already paid deposits on. While manufacturers struggle to certify and deliver aircraft, airlines are hemorrhaging money operating the ones they already have. A joint study by IATA and Oliver Wyman quantified the damage. Supply chain challenges cost the global airline industry over $11 billion in 2025 alone. The breakdown is precise and painful. Approximately $4.2 billion in delayed fuel savings because airlines are forced to fly older, less efficient aircraft they had planned to retire. Another $3.1 billion in higher maintenance costs to keep aging fleets airworthy. An additional $2.6 billion in excess engine leasing costs as power plants spend longer in overhaul shops. And $1.5 billion in spare parts stockpiling as airlines hoard inventory to protect against unpredictable supply disruptions. The global aircraft backlog stood at approximately 17,000 jets in 2024. Average fleet age has risen to 15.1 years. More than 47 aircraft sit in storage, many of them waiting for engines or parts that simply do not exist in sufficient quantities. Airlines depend on a reliable supply chain to operate and grow their fleet's efficiency. Now they face unprecedented waits for aircraft, engines, and parts alongside unpredictable delivery schedules. This is the environment in which Boeing and Airbus must somehow find the resources, the engineering talent, and the production capacity to design something entirely new. Historical precedent suggests that developing a clean sheet narrowbody aircraft costs more than $10 billion, potentially more if delays persist. The Boeing 787, the last true clean sheet commercial aircraft, was originally budgeted at a fraction of its final cost. Development spiraled to more than $32 billion. Total program costs, including customer compensations for a 3.5-year delay, reached an estimated $50 billion, according to Leham News and Analysis. The 787's cost overruns were among the reasons why Boeing chose to re-engine the 737 rather than spend $15 to $20 billion on a new clean sheet design. That decision to save money by avoiding a clean sheet design led directly to the engineering compromises that produced MCAS. Former Boeing CEO Dave Calhoun acknowledged the scale of what comes next before stepping down. He stated publicly that Boeing's next airplane would require a $50 billion investment. But whether the number is $15 or $50 billion, the financial challenge is extraordinary for both manufacturers. Boeing carried over $54 billion in gross debt at the end of 2025, funding a massive clean sheet program, while servicing that obligation requires either unprecedented cash generation, significant equity dilution, or government intervention. Airbus is in stronger financial shape, but even Airbus is conservative about a new aircraft program, knowing the range of issues the European manufacturer is currently facing. The significance of the next airplane isn't really about the airframe, and it isn't really about the money. It's about what the engine manufacturers can deliver, and when, because that single variable dictates everything else. A 15 to 20% fuel efficiency improvement could justify the development of a new aircraft type. That threshold is the minimum needed to offset the massive costs of fleet transition, new pilot training, new maintenance infrastructure, new spare parts inventories, and new ground support equipment. Customers dictate the aircraft market. Don't believe me? Take a look at the A330-800 or the A319neo or the Boeing 737 MAX 7, which is almost exclusively ordered by Southwest Airlines, and the 7878, which has received 8 orders since 2020. 8 total 7878s, not orders consisting of dozens or more aircraft. Achieving 20 to 30% total improvement, which both Airbus and Boeing are targeting, requires roughly 15 to 20% to come from propulsion alone. The remaining gains come from aerodynamic improvements like laminar flow wings, lighter composite structures, and optimized flight systems. The problem is that next-generation engines do not yet exist in mature form. CFM International, the GE Aerospace Safran joint venture that powers most of the world's narrowbodies, is developing advanced architectures, including open rotor concepts that promise dramatic efficiency gains. But open rotors present enormous integration challenges: noise certification, structural mounting, bird strike vulnerability, and passenger acceptance of exposed fan blades visible from the cabin window. Pratt & Whitney, maker of the geared turbofan that powers the A320neo family, is struggling with durability issues on its current engines. Hundreds of aircraft sit grounded worldwide, awaiting GTF inspections and repairs. Developing a next-generation successor while fixing fundamental reliability problems on the current product stretches engineering resources to their breaking point. Rolls-Royce, historically absent from the narrow-body market, but in March 2026, the British company confirmed that it secured investment for its UltraFan 30, its next-generation engine, specifically for narrow-body aircraft. You see, neither Boeing nor Airbus can launch their next airplane until the engines are ready, and the engines won't be ready until the 2030s. This creates a brutal strategic paradox. Both manufacturers know they need to move, both know they cannot move yet, and every year of waiting deepens the fleet age crisis, compounds airline operating costs, and erodes the engineering talent base needed to execute the program when it finally launches. Because Boeing has not launched an all-new design since 2004, a generation of Boeing engineers will never have designed a plane from scratch. The institutional knowledge required to orchestrate a clean sheet build is actively decaying. The competitive dynamics between Boeing and Airbus have never been more asymmetric. Airbus has formally named its replacement program the Next Generation Single Aisle, or NGSA. The French government has committed €300 million annually from 2024 to 2027, totaling €900 million to support the technological foundation for this aircraft. Airbus is actively developing building blocks under its E-Action program, exploring advanced open rotor derivatives, hybrid electric systems, and hydrogen propulsion concepts under its Zero E initiative. Boeing's position is defensive, consumed by MAX certification delays, 777X delivery pushbacks, and an order backlog it cannot fulfill fast enough. Boeing's product development pipeline has been effectively frozen for 2 decades. CEO Kelly Ortberg has begun preliminary studies for a 737 successor. But Boeing publicly maintains it is not close to launching a new airplane. This asymmetry creates a first-mover problem. If Airbus launches its NGSA first and captures the next wave of narrowbody orders, Boeing risks permanent marginalization in the segment that generates the majority of commercial aviation revenue. But if Boeing rushes to launch prematurely with immature technology and a weakened engineering culture, it risks repeating the catastrophic pattern that produced the MAX crisis. The company literally cannot afford another clean sheet failure. Too much debt. What Boeing and Airbus are really deciding is not which airplane to build. They're deciding what kind of companies they will be for the next 50 years. The manufacturer that successfully designs, certifies, and scales production of the dominant 2040s narrowbody will secure economic supremacy for half a century. The one that falters may never recover. This isn't hyperbole. The narrowbody market is the economic engine of commercial aerospace. It funds wide-body development and hundreds of thousands of jobs across dozens of countries. Whoever controls the narrowbody production line controls the industry's center of gravity. And the stakes extend beyond the manufacturers themselves. Airlines operating aging fleets are burning billions in excess fuel and maintenance costs every year. Environmental targets depend on the 20 to 30% efficiency improvements that only a new generation aircraft can deliver. Regulators face the impossible task of ensuring safety, while an industry strains under the weight of deferred modernization. The Airbus A380 serves as the cautionary tale. Developed at a cost of 18 to 25 billion euros, it entered the market and failed to achieve profitability and was eventually discontinued. A single wrong bet on technology, timing, or market demand can erase decades of industrial investment. When the first clean sheet narrowbody finally rolls off the production line, it will represent not just a new airplane, but the resolution of a crisis that consumed an entire industry for more than a decade. Two manufacturers, hundreds of billions of dollars, decades of engineering, thousands of suppliers across dozens of countries. The question isn't whether the new airplane will get built. It will. Airlines demand it. The economics require it. The climate cannot survive without it. The question is whether the industry that builds it has really learned the lessons of what happens when you try to avoid making the hard choice.